Alright, thanks for joining us for this second video in chapter 6, where we started thinking about an actual organic reaction, namely the SN2 or nucleophilic substitution by molecular reactions. And as a chemist, right, like we want to be able to predict whether excuse me, whether a particular reaction happens. If you look at two molecules structures, would they react with each other? Would they react through SN2 reaction specifically? That's the kind of things I want you to be able to do for our class. And so we want to think about the factors that influence this SN2 type reactions. And I don't know what happened with the symbol here, sorry, but just a bullet points. There's 4 factors we should think about. Is the nucleophile very nucleophilic? That's a key. If it's not very nucleophilic, it's not suitable for SN2. It's not a good candidate, right? And often the nucleophilicity of the nucleophile correlates with basicity. So it's not a 100% accurate rule, but in general, the more basic something is, the more nucleophilic it is. And then there's the solvent factor, and then like how good of a leaving group you've got, and then the steric factor that we'll think about. Okay, so first the nucleophile, which arguably is one of the most important factors here. It has to be an anion at least, so hopefully it's not surprising, because nucleophile loves positive charge, or neutral species with at least some sort of lone pair, right? If you don't have any of that, it really can act as a good nucleophile. So let's first think about the neutral nucleophile, like sort of in a generic sense, or maybe we'll actually think about an actual example, say methanol, which has this structure. That's the alcohol that you should not drink. If you do, you'll go blind and die and whatnot. And methanol arguably is a little bit nucleophilic, at least. Why do I say that? Well, because it does have an atom with some lone pairs on it. Okay, and then this is kind of a good electrophilic substrate, because you've got a halide that of course is pulling on the electrons. It wants to, it's partially negative, partially positive on the carbon. What that means is iodide wants to kind of sort of run away with these electrons, you know, if he could, because of its electronegativity. That's what all halides want to do. And so then oxygen as a nucleophile would be attracted to this partial positive charge. And so if the reaction were to happen, we should see those arrows, and those this bond forming and this bond breaking. With that, you should get an intermediate that looks like that. Notice I tried to depict the inversion at this carbon. This inversion is kind of like the same thing that happens if you are holding an umbrella in a windy place like Laramie, right? The umbrella could sort of flip, and so it's flipped over. That's sort of what you should picture here. And then the leaving group in this case, of course, is the iodide, right? And then don't forget the formal charge on this oxygen. So what happened here? We went from 2 species that were totally neutral to a charged species, and so for that reason, this is actually slow. So we went from totally neutral to charged. So this is a slow reaction. Why? Because to go from neutral, which is more stable, and then to charged, bunch of charged species, that would create a high activation energy, right? Like if you think of the reaction energy diagram, here's your reactants, here's the product or this intermediate that's charged. I'm talking about this species. That would be a fairly high energy species, right? So that means you have to overcome this big activation energy. So this is a high activation energy process. Remember that stands for high activation energy. And if you have a high activation energy, that reaction tends to be slow. Now, what if you have an ionic nucleophile? Here's a methoxide. In the same electrophilic substrate. Now, I hope you could appreciate that this is actually even more nucleophilic than the neutral methanol because of the negative charge, and hopefully the name makes sense too. Remember from Chem that when you have a negatively charged material or species, the name should end with either IDE, like a chloride, iodide, methoxide, or ate, like sulfate, acetate, that sort of things. So this would, of course, be able to do that SN2 reaction. And the end result would look like that. And of course there's the iodide leaving group. So that's your leaving group. But this time what we notice, of course, is we went from at least one of these two pairs was charged. We went to a neutral product, and so that is actually a very good thing, right? So we went from charged to neutral. So these two things combined to become this molecule. We went from charged to neutral, and so therefore this time we should have a sort of reaction energy diagram that looks like starting with a high energy and then ending with low energy. And so for that reason, this is not going to be this is not going to be a high activation energy situation, and so this is going to be low. Low activation energy. One other thing that this tells you is that this methoxide now is a better nucleophile. Okay, so what this example sort of shows you is in general, the higher the basicity, like more negatively charged or whatever, usually higher the nucleophilicity. Right, between methoxide and methanol, methoxide is of course more basic because this negatively charged methoxide would be more likely to pick up a proton, positively charged, than neutral methanol. So, and then another factor about nucleophiles that we haven't discussed a lot is the bulkiness, which will come up later again. If you can reduce the bulkiness of the nucleophile, the nucleophilicity is usually better, lower activation energy situation. This is a pretty good nucleophile because it's not very bulky, it's not very big, whereas if you replace this methyl group with T-butyl or something like that, that's really bulky and then it would not be very nucleophilic. So And here I just want to kind of list typical examples of nucleophiles, and we might sort of categorize them into like different levels of nucleophilicity. Now, in this context, when we say poor nucleophiles, that doesn't necessarily mean that they could never act as a nucleophile. It's just that it's not as good as, say, a good nucleophile. So if there's a good nucleophile and a poor nucleophile in the same mix, guess which is going to do the SN2 reaction? Well, that's going to be the good nucleophile. The poor nucleophiles often do not initiate an SN2 reaction. It can do things like SN1 reaction, which we'll talk about a little later, but with that background, let's think about some of the good nucleophiles, and roughly I'm going to list them in the order of decreasing nucleophilicity. So some of the best nucleophiles that you'll ever work with would be anionic sulfur compounds. So these are thiolate compounds. It's called thiolate because it's a thiol that has become negatively charged. Thiol is SH, remember, and once that becomes negatively charged, it's not only electron rich, so it's good for nucleophilicity, but remember, bigger atoms tend to be, right, like we talked about, that bigger atoms tend to make the nucleophile more polarizable, and so for that reason it becomes more nucleophilic. And so for that reason, these sulfur nucleophiles, they're excellent nucleophiles. Another really good one, iodide, for similar reasons. It's got negative charge, so electron rich, so that's good for nucleophilicity, but also it's big, meaning it's very polarizable. And another might be the alkynide or acetylide type of anion. These are particularly good because remember the molecular shape here is sp linear, and so this has kind of like a torpedo type of a shape, which makes it so not bulky, that it's very good. Alkynide is sort of the IUPAC name for this, and similarly cyanide, similar structure, is a pretty good nucleophile. And maybe after that comes alkoxide, so like a methoxide that we saw is kind of similar. Hydroxide is kind of a similar situation. The only difference is here R is some sort of a carbon or alkyl group. So these are alkoxide. And of course, the one on the right is hydroxide. And then this, you might not expect this, but neutral phosphines they're pretty nucleophilic because, again, phosphorus has a lone pair. It doesn't have a negative charge, but at least it's very polarizable. It's a fairly big atom. And then comes substituted amines. So, oops, that's not right. So either doubly substituted or at least singly substituted amines. Those are pretty good nucleophiles because because of these alkyl groups, which are fairly electron rich, that they inductively donate electrons to nitrogen, which of course is nucleophilic. So those are good nucleophiles. Now the moderate ones, maybe some examples would be bromide, chloride is not as good as bromide, and I might be a little bit off on this ranking, but the sulfides are pretty good, even though it's neutral. And then acetate or carboxylate, right, is not like an excellent nucleophile, but it's a decent nucleophile. again, because of negative charge, but also because of through resonance, it's very polarizable. And it depends on how bulky the R group is, but the triply substituted or tertiary, these are called tertiary amine, is a decent nucleophile. If the R group is small, it's actually a pretty excellent nucleophile, but if it's big, it's not going to be as nucleophilic. And again, so this is kind of a double-edged sword. It increases the nucleophilicity because it donates electrons to nitrogen, but then because of the bulkiness, that would decrease the nucleophilicity. Now, some examples of poor nucleophiles. Among the halides, that would be fluoride, and the reason for that, of course, is fluorine is so electronegative that it wants to keep all these electrons to itself rather than sharing them in the form of nucleophilic attacks. Then sort of neutral things like water is somewhat nucleophilic, and maybe I should say just generically alcohol is also somewhat nucleophilic, and they're not strong enough to cause an SN2 reaction usually, but I just want you to know they're somewhat nucleophilic. They can do, maybe we'll say, they're not good enough for SN2, but these can do SN1. That becomes important later. If you try to see some trends here, right, like when you have similar related things like thiolate and sulfide, you notice the neutral species is not as nucleophilic as, of course, the anionic species, like alkoxide and alcohol, right? Another trend you see across this table is for the halides, at least, you would see this trend. And this has to do with polarizability. And electronegativity. Hope that makes sense. The bigger atoms or ions are more polarizable. And these fluorine, chlorine, they're very electronegative, so they don't want to share the electrons anyway, so that reduces their nucleophilicity. Okay, so one of the goals here, I want you to be able to recognize a good nucleophile when you see one. And these guys especially are very good for SN2. And sometimes you could see SN2 with some of the moderate nucleophiles if all other conditions are pretty good. Okay, so in the next videos we'll talk about some other factors like the solvent factor.